Hello my friends and welcome back to the You Can Do TV channel. Heavier bridge segments can actually speed up installation when built as standardized box girders. Structural steel and pre-stressed concrete are formed into pre-engineered box girders long before arrival at the installation site. Pre-stressing introduces internal compression that counteracts tensile stress during service. Raw materials pass through 9 stages and 18 procedures over a total of 42 days. Each step locks in structural strength that cannot be adjusted later. Dimensional tolerances are verified at multiple checkpoints during fabrication. The controlled sequence keeps dimensions consistent across every unit. Every girder weighs about 1,000 tons and is built to withstand severe weather and heavy dynamic loads. Load ratings account for high-speed train forces, wind exposure, and long-term fatigue performance. 1,000 tons per segment changes how you think about scale. Transport and lifting systems position the segments onto piers, where crews bolt them together to create a continuous bridge deck. Bolted connections distribute forces across adjoining segments through engineered joint interfaces. This modular method accelerates assembly while maintaining strict quality checks. Prefabrication shifts complex fabrication tasks away from the erection corridor. Elevated alignment reduces ground interference and supports smoother high-speed travel. Seeing entire spans align in sequence feels unreal at first glance. Expansion continues to meet rising demand, supported by a standardized fabrication system designed for efficiency and durability. Scalable production capacity aligns output with ongoing network expansion targets. Assuming tunnels must be bored in place overlooks the efficiency of prefabricated box sliding methods. Moving a 70-meter prefabricated tunnel beneath an active highway within a single weekend requires synchronized excavation, sliding systems, and strict staging control. The tunnel structure is cast in advance using reinforced concrete, forming a rigid box capable of carrying traffic loads above. Precasting off-site shifts most heavy work away from the highway closure window. Meanwhile, crews prepare the receiving pit and approach trench beside the roadway. Soil support walls and temporary foundations are installed to stabilize the excavation zone. Once traffic is diverted, the road surface is removed and the trench opened to full depth. Hydraulic jacks and sliding tracks are positioned under the tunnel box. The structure is then pushed laterally into place using controlled force. 70 meters of concrete moving sideways under a highway feels unreal. Alignment checks continue throughout the slide to keep the tunnel centered. After positioning, backfilling restores ground support around the structure before pavement layers are rebuilt above. Completing all of this in one weekend leaves no room for hesitation. Final compaction and surface finishing reopen the highway to traffic, while the underpass awaits full operational use. Core rebar installation and post-tension slab construction form the primary structure of this high-rise building. Core reinforcement is detailed to match the structural drawings for wall thickness and bar spacing. Activity centers on the P2 level, which functions as parking above the ground floor and ties into the slab above B1. Vertical reinforcement rises within the concrete core footprint. Core walls provide the primary lateral resistance system for the tower. Crews align and secure each bar intersection before forms close around the cage. Bar ties maintain spacing, and prevent displacement during concrete placement. Steel density increases toward coupling beam zones. Beyond the core, deck crews arrange PT tendons along engineered drape profiles. Anchors set at slab edges, and strand tails extend for stressing. Tendon profiles follow calculated high and low points across each span. Post-tension tendons introduce compressive force that counteracts tensile stresses in concrete. Delay strips remain open around the core perimeter. Delay strips permit stage pours and reduce restraint as the structure shortens over time. Strip widths correspond to specified joint dimensions in the structural plans. Stud rails are set at column lines to strengthen slab column connections. Stud rail systems improve punching shear resistance at concentrated load points. Drop caps thicken slab regions over columns, redistributing loads into the deck. Drop caps increase shear capacity without adding full depth slab thickness across the floor. Cap dimensions reflect column size and calculated shear demand. In-beds for precast panels are marked and fixed before the pour. Mechanical vault zones are framed, including an electrical service vault and blockouts reserved for fire department connections. Blockout dimensions match utility and code clearance requirements. Coordination among trades intensifies here. One misplaced sleeve would create chaos. No room for guessing. Concrete placement secures reinforcement, tendons, and embedded items into a unified slab. Consolidation eliminates voids around stud rails and anchors. Vibration ensures full encapsulation of reinforcement within the concrete matrix. After curing reaches the specified strength, stressing crews tension the PT strands in a defined sequence. Stressing operations follow calculated elongation targets to verify applied force. Gauge readings confirm each strand meets design values. The slab compresses slightly under load introduction, locking the system together. Ramp geometry transitions through a warped connection that meets the sloping parking deck. Sloped slabs require adjusted tendon profiles to maintain uniform structural performance. The P2 parking layout integrates with the core to transfer gravity and lateral loads downward. Load paths extend from slab bands into core walls and continue toward the foundation system. In selected areas, niche zones and service corridors align with the structural grid to avoid interference. Every penetration, every anchorhead, every bar splice feeds into the same objective continuous load transfer from deck to core to foundation. That layered coordination really brings the whole frame together. Same speed, same tightness, light and heavy models side by side. This comparison tests different brand rebar tier machines under identical tying conditions. Each tool is loaded with matching tie wire and applied to the same rebar grid layout. The nosepiece aligns against intersecting bars before activation. Consistent wire tension defines final knot firmness. Oh, that wrap snaps in instantly. Both compact and heavier units complete the twist and cut cycle in one motion. Finished ties are inspected for loop symmetry and wire tail length. This solid masonry house uses a full reinforced slab instead of a basement foundation. The house footprint is staked out before excavation removes topsoil and unsuitable soil layers. Proper subgrade preparation directly determines structural stability over decades. Compaction equipment densifies the ground to meet load-bearing specifications. Next, strip footings are installed beneath future load-bearing walls. Reinforced concrete footings distribute wall loads evenly into the soil. Formwork frames the slab perimeter, while thermal insulation panels are positioned below. Plumbing and electrical conduits are laid out before concrete placement. Pre-installing utilities prevents structural cutting after curing. Concrete is poured across the entire footprint, forming the foundation slab that serves as both structural base and ground floor support. Crews level and screed the surface to the specified thickness. Wow, that single continuous pour locks everything together. After curing, the structure gains a stable platform for wall construction. Total time for earthworks and slab installation, 3 days. A monolithic slab ensures uniform load transfer for the two-story superstructure. Traditional straight-line screeding wastes time on circular pads, and the Laura Lightning Strike roller screed proves it by completing an 82-foot grain bin pad in one sweeping motion. Crews position the circular layout at a 41-foot radius, marking the bolt pattern so the future 78-foot bin will anchor exactly where planned. Two 20-foot tubes joined with a 2-foot extension create 42 feet of screed span, allowing the roller to bridge wide sections without constant repositioning. Concrete is distributed evenly across the form, and the electric motor powers the roller forward, striking off excess material while blending aggregate into a uniform layer. Rakers spread the mix ahead of the screed, and a vibrator operator consolidates the slab to remove trapped air pockets. That coverage speed changes the math on big pours. The screed moves along the circular guide, shaving high spots and filling low areas in a steady sweep. Bolt guides simplify alignment, reducing the risk of costly corrections later. In the end, the 82-foot pad stands as a solid foundation built to support heavy grain loads year after year.
One precise wedge line can split a multi-ton granite block clean in two. Raw granite blocks are positioned on stable ground, aligned with their natural grain so the fracture can follow internal structure instead of resisting it. A straight wedge path here saves hours later. Steel wedges are inserted into pre-drilled holes, spaced evenly along the marked split line. Hammer strikes drive the wedges deeper, building internal pressure across the stone. Granite does not flex. Stress accumulates until a clean crack travels through the block. That sharp fracture still catches you off guard. The oversized mass separates into smaller sections, sized for secondary processing, such as splitting into paving elements or cut stone pieces. Operators adjust wedge spacing according to thickness and visible fissures in each block. Wider spacing can shift the fracture offline, while tighter spacing increases force requirements. Granite pushes back in its own quiet way. Once divided, each section is checked for structural consistency and sorted by intended application. The reduced stone units are then loaded onto heavy transport vehicles from the fleet for delivery to customers who will continue shaping them into finished natural stone products. Controlled force, practical experience, and repeatable technique convert raw extraction blocks into manageable material. When a block opens exactly along the mark, that feels seriously good.
Discarded plastic and glass can become load-bearing concrete bricks through mechanical recycling. Plastic and glass waste recycling into concrete brick follows a defined mechanical sequence using a plastic shredder, glass crusher, multi-purpose mixer, and concrete brick molder. Plastic waste enters the shredder first, reducing larger pieces into smaller fragments suitable for blending. Uniform particle size improves consistency in the final mix. Glass bottles and vials move through the crusher next, breaking into crushed glass granules. Crushed glass replaces part of traditional aggregate in the brick composition. Wow, trash just shifted categories completely. Measured batching follows. 1 bucket of crushed glass, 1 bucket of shredded plastic, 1 bucket of sand, and half a bag of cement enter the mixer. Balanced proportions maintain structural bonding within the composite material. The rotating chamber blends the components into a workable mixture. The prepared blend transfers into the concrete brick molder. Compression shapes the mixture into solid paver forms. Compaction increases density and load-bearing capacity. Seeing discarded material pressed into solid blocks feels unreal. Curing allows the bricks to harden before use. The finished product combines recycled content with conventional strength characteristics.
People often think drainage concrete needs heavy machinery, but this process relies on controlled mixing, precise ratios, and timing to achieve reliable drainage performance with plasbeton materials. The video explains the production workflow for Dranazny plasbetony, focusing on how epoxy resin binds graded aggregate into a stable drainage layer. Material preparation comes first, with aggregate measured carefully to match the specified structure. Binder is then introduced, following the defined ratio of 10 kilograms of epoxy to 160 kilograms of aggregate, ensuring proper coating without excess resin. Mixing continues until the surface of each stone is evenly covered, not flooded. This is the moment where mistakes quietly multiply if attention slips. The blended material is transferred for placement, while its workability window remains open. Compaction shapes the layer while preserving voids for water flow. It looks simple, yet every step quietly insists on discipline. The result is a drainage concrete that supports load while allowing water to pass efficiently, avoiding trapped moisture and long-term damage. That balance always feels slightly tense, like walking a line you cannot see.
Handmade tiles come to life here through old-world craft, shaped entirely by human touch rather than automated lines. Clay bodies are prepared in measured batches, mixed to achieve consistent density before being pressed into molds, one piece at a time. Hand forming allows subtle variations that machines simply cannot reproduce. Each tile is lifted from its mold and laid out to dry under controlled airflow, preventing warping while moisture gradually leaves the surface. The drying stage requires patience, allowing the structure to stabilize before heat exposure. Artisans monitor texture and firmness to decide the right moment for the next phase. Small surface marks are smoothed by hand to maintain a balanced finish. Consistency across batches depends on disciplined timing and controlled humidity. After drying, edges are refined and surfaces adjusted to maintain dimensional balance. Bisque firing strengthens the structure and sets the base for glazing. Technicians apply custom glazes by hand, layering tones to create depth across every piece. No two tiles leave the table exactly alike, and that individuality becomes the whole point. A second kiln cycle fuses glaze in clay into a durable finish suited for kitchens, baths, and commercial interiors. Quality checks follow cooling, confirming thickness, color consistency, and surface integrity. Seeing stacks of tiles built one by one makes mass production look almost anonymous. Orders are packed according to custom specifications, reflecting the studio's commitment to tailored design. The result is a surface material rooted in tradition, yet adapted for modern architectural demands, proving that hands-on methods still compete in a highly industrial world. Seeing broken glass regain purpose changes how waste is viewed. Mixed glass collected from curbside bins enters a sorting line that removes contaminants before crushing. Screens separate fragments by size. Magnets extract stray metals, and air systems lift away paper or plastic residue. The cleaned cullet moves to storage, later supplied to bottle and fiberglass production, closing the material loop efficiently. Each stage ensures recycled glass meets strict manufacturing standards before returning to industrial furnaces. This controlled sequence reduces landfill dependence while supporting continuous glass manufacturing. Discarding surplus concrete wastes material that could be formed with block mold systems. Concrete block molds shape leftover mix into stackable units designed to fit together like building bricks. Each mold cavity determines the final block dimensions and interlocking profile. Fresh concrete is poured into the steel mold, filling corners and edges completely. Excess material is leveled off before curing. Surplus material suddenly becomes usable stock. What a turnaround! Once the mix gains strength, the mold is lifted, leaving solid blocks ready for handling. Durable mold construction supports repeated casting without deformation. Different mold sizes allow flexible output for retaining walls or storage bays. Modular geometry enables stable stacking without mortar joints. Instead of sending material away for disposal, the same concrete becomes a reusable structural element. Now that's a practical upgrade in resource use. Surface excavation is not required when the UB40 microtunneling machine performs pipe jacking underground. The launch shaft is prepared first, aligning the machine with the planned tunnel axis. Accurate initial alignment determines the final pipeline trajectory. Survey control points establish horizontal and vertical reference data for setup. Hydraulic jacks position the cutting head against the soil face. Thrust force is regulated to match ground resistance conditions. Excavation advances as the rotating cutter head breaks ground while spoil is transported back through a slurry circuit. Continuous slurry flow stabilizes the tunnel face and removes excavated material efficiently. Slurry pressure balances surrounding soil to maintain tunnel stability. Guidance systems monitor line and grade in real time, adjusting steering cylinders to maintain direction. Steering corrections are executed through articulated joints within the shield. Behind the machine, prefabricated pipe sections are lowered into the shaft and pushed forward using a jacking frame. Pipe segments are manufactured to specified diameter and wall thickness. Pipe jacking transfers thrust evenly to prevent joint stress. Each new segment connects to the previous one, extending the pipeline incrementally. Sealed joints maintain pipeline continuity under compressive load. Progress continues until the receiving shaft is reached. What a clean way to go underground without tearing up the surface. The result is a precisely installed utility line with limited environmental impact.
The operation begins with the stabilization of the pipe using modular scaffolding systems, ensuring both structural support and operator safety. A portable pipe cutter is positioned along the marked initialization point and reference lines, which are established based on pre-engineered connection geometries to maintain dimensional accuracy. Lifting and alignment are facilitated by a safety-certified overhead crane, allowing controlled pipe placement within the cutting zone. A rotator equipped with a variable speed controller ensures uniform pipe rotation, critical for maintaining cut consistency across the full circumference, especially in field conditions where tolerances are tight. Prior to the actual cut, a dry run is conducted to verify cutter alignment, rotator performance, and the integrity of all mechanical interfaces. This step mitigates the risk of deviation, thermal distortion, and equipment malfunction during cutting. Following successful dry validation, the cutting process is executed with continuous monitoring of rotation speed, blade feed rate, thermal buildup, and vibration levels. Upon completion, a final check is performed to assess cut perpendicularity, edge finish, and compliance with connection specifications. Additional steps such as bevel inspection, edge cleaning, and burr removal may be carried out to prepare the surface for welding. This systematic procedure ensures the pipe ends meet stringent tolerances, reduces rework, supports high-integrity offshore joints, and ensures long-term performance under harsh environmental conditions. The reactor pressure vessel installation at Akuyu NPP Unit 1 represents a key milestone in the plant's nuclear construction phase. Deepwater prospects often stall under pressure, but Jack/St. Malo advanced through coordinated drilling, subsea installation, and floating production integration. Exploration wells confirmed high-pressure reservoirs beneath thick salt layers. Deepwater conditions pushed equipment limits. Engineers advanced drilling systems, completion design, and subsea layouts to manage extreme pressures. Every approval carried weight. Installation teams connected wells to a floating production unit, aligning flow lines and risers. Suddenly, first oil arrived after a decade of persistence.
Some believe offshore platforms rest on the seabed. The Asta Spar actually floats upright, held steady by a massive vertical hull that extends deep below the surface. The Spar substructure rises 200 meters tall, weighing 46,000 tons. A deep draft spar provides stability by lowering its center of gravity far below wave action. That scale alone changes the entire engineering equation. This depth is no joke. Fabrication of the hull progressed in a horizontal position using mega-block assembly. Large structural sections were constructed at ground level, then joined into one cylindrical body. Building in horizontal orientation improves welding access and structural alignment control. Once complete, the hull prepared for transport before upending offshore. The topside, weighing 24,000 tons, houses conventional gas processing systems. Piping crews advanced module by module ahead of hydro testing and valve installation. Completing piping networks early reduces commissioning delays during final integration. 2,000 workers coordinated mechanical, electrical, and structural tasks. What a logistical push! After hull transport, the structure was upended vertically and mated with the topside. The connection point between substructure and topside required exact load transfer design. Interface engineering ensures balanced stress distribution between floating hull and processing deck. Subsea equipment installation reached depths never previously attempted in the region. A 482-kilometer polar-led pipeline extended gas export capacity across long offshore distances. Together, the Spar platform and pipeline established infrastructure capable of supporting future tie-ins and long-term field expansion under demanding marine conditions.
Valaman jacket reached offshore installation at 150 tons, nearing crane vessel lifting limits. This mass positioned the structure close to the upper threshold of single-lift offshore operations. Concept development translated feed data into detailed engineering, defining structural dimensions, load paths, and impact resistance criteria. Load path mapping identified primary stress corridors through legs and braces. Weight control dominated every calculation. Total structural weight reached approximately 150 tons, placing it near crane vessel capacity limits. Finite element analysis verified stress distribution under extreme sea states. Designers refined bracing geometry and joint reinforcement to manage stresses while limiting mass growth. Brace angles were adjusted to balance axial and bending forces. Boat impact resistance required structural modifications due to its placement along the shipping route. Impact load scenarios directly influenced node thickness and brace configuration. Node reinforcement increased localized energy absorption capacity. Fabrication advanced with the first steel cutting milestone, marking the transition from drawings to physical assembly. Steel plates were traceable by heat number throughout production. Plate sections moved through cutting, forming, and welding stations, gradually forming large tubular sections and node clusters. Sequential block assembly reduced distortion during heavy weld operations. Weld sequencing followed predefined heat input limits. Modules combined into larger jacket sections within the yard. Height extended to roughly 160 meters, with a footprint of 45 by 45 meters and a top frame measuring about 25 by 35 meters. Dimensional surveys confirmed vertical alignment during stacking. Seeing that scale assembled on land feels unreal for a split second. Then the dimensions register. Loadout preparations followed structural completion. Support stools aligned beneath key load points, distributing mass evenly onto the transport barge. Accurate center of gravity calculation governed skid transfer procedures. Load transfer analysis validated barge deck strength margins. Hydraulic skid systems shifted the jacket toward the barge deck in controlled increments. Tow-out operations required stable C-fastening to prevent structural movement during transit. C-fastening structures were welded to predefined restraint points. The voyage lasted around 3 days under managed towing speed. Offshore installation entered its critical phase upon arrival. A heavy-lift crane vessel positioned above the site and connected lifting slings to designated pad eyes. Lift planning accounted for hook height, sling angle, and dynamic amplification factors. Sling tension equalization was verified prior to hoisting. The jacket cleared the barge and moved vertically toward the seabed target. Reaction forces transferred gradually into pre-installed piles during set-down. Pile sleeves guided alignment during final penetration. Installation extended between 2 and 2.5 weeks, including pile driving and final leveling. Then came that moment. Steel settled into its final offshore position, and years of coordination turned into standing structure. Across roughly 50 weeks of fabrication and nearly 2 years of combined effort totaling about 350 man-years, coordinated engineering, procurement, fabrication, transport, and installation converged into a single offshore foundation. The Valamon jacket stands as one of the largest and safest jackets constructed for harsh marine service. Integrated project sequencing minimized schedule deviation while maintaining structural integrity targets. Delivery occurred ahead of schedule by several days, concluding a build cycle that pushed structural scale and lifting capacity to their upper margins.
One more Shea CFA continuous flight auger pile can be installed without a single steel casing on site. This system advances a continuous flight auger into the ground to the required depth without temporary or permanent casing. As the auger penetrates, soil is conveyed upward along the flights and removed at the surface. Continuous monitoring of depth and torque confirms the pile reaches design capacity. Once target depth is achieved, concrete is pumped through the hollow stem while the auger is steadily withdrawn. That upward movement replaces excavated soil with concrete in one controlled sequence. Seriously, no second chances here. Maintaining positive concrete pressure prevents voids and soil collapse. Reinforcement steel is then inserted into the fresh concrete to complete structural requirements. The method limits vibration and keeps noise levels low, making it suitable for sensitive sites. Production efficiency improves because casing handling is eliminated. Reduced equipment footprint also frees up valuable workspace. Whoa, that streamlined setup really shifts the pace on site. Zero-energy housing is no longer a concept piece. Insole wall and solar span panels are pushing it into everyday residential construction. Factory-controlled panel production stabilizes dimensional consistency across wall assemblies. This system replaces conventional framing and layered insulation with structural insulated panels engineered for thermal control. Each panel combines structural skins bonded to an insulating core under controlled pressure. Wall sections arrive factory-made, sized for fast alignment on site. Fewer components mean fewer installation variables to manage. Panel joints are sealed to maintain continuity of the insulated envelope. Crews position each insole wall panel, secure it to the slab and adjoining panels, and seal joints using the standard internal plastering method. Mechanical fastening ties panels directly into the structural base. Pre-cut service ducts are already formed inside the core, allowing electrical conduit to slide through without chasing walls. That shortcut alone saves serious labor. Wait, that's a big shift. Integrated ducts maintain wall integrity without additional cutting. Roof installation integrates structure, insulation, and ceiling in one solar span assembly. The roof panel spans between supports, while enclosing insulation within its profile. Panels are craned into place and fixed along the supporting frame, forming an insulated envelope without adding separate ceiling batts. Thermal bridging is reduced because insulation remains continuous across the structure. Continuous insulation limits conductive heat transfer through framing lines. External finishes follow, including rapid application of Dulux Acrotex for a seamless protective coating. A uniform coating thickness strengthens surface durability against weather exposure. The exterior surface supports varied architectural styles, so design flexibility stays intact. Australia's 6-star energy efficiency requirement drives higher performance standards, and this panel system answers with measurable thermal resistance. Lower air leakage directly improves energy performance over the building's lifespan. Construction time drops since multiple trades are consolidated into fewer installation stages. Whoa, that compressed schedule really changes project planning. The completed structure delivers reduced operational energy demand while maintaining structural integrity and interior comfort. A single 3D scan can drive the entire timber production workflow to final building assembly. The sequence opens with a 3D scan of the site or structure, generating accurate geometry for planning. Design software converts that scan into detailed production drawings and CNC files. Cutting lines transfer directly to automated timber machines, shaping beams and panels to specification. CNC processing reduces manual measurement on the shop floor. Structural elements are labeled and organized for sequencing. Honestly, that digital handoff tightens everything up. Prefabricated components move to staging for transport. On site, crews position each timber unit according to the digital plan. Wow, seeing parts fit without field trimming changes expectations. One tall concrete silo stands for decades, yet a few strategic cuts decide the exact second it falls. Instead of blasting charges, the structure is weakened step by step at the base. Openings are cut into the lower wall to direct the fall line. That notch placement decides everything about the direction. Steel reinforcement is exposed and severed, reducing resistance on one side, while the opposite wall remains intact to act as a hinge. Structural imbalance increases progressively until gravity overcomes the support. The arm applies steady pushing force once the cuts are complete. Pressure increases in a controlled manner through the boom and stick. Excessive thrust at the wrong angle could shift the fall direction. Then the balance changes. The tall cylinder begins to lean, concrete fractures along the prepared line, and gravity takes control. All that height disappears within seconds, while the surrounding ground outside the target area remains undisturbed.
The larger the feed, the steadier the output becomes with the Kleeman MOBICONEMCO11, a mobile cone crusher built to refine secondary material into a consistent final product. Material arrives either directly from a primary crusher or by wheel loader, dropping into a 15.7 cubic yard hopper designed to handle continuous supply. A vibrating feeder lined with wear-resistant sheets regulates the flow before it reaches the 44-inch cone. Variable cone drive settings adjust throughput, allowing operators to match production demands without overloading the chamber. Controlling the feed like this keeps product size uniform and protects internal components. An electric magnet extracts ferrous metals, while a metal detector identifies non-ferrous contaminants ahead of the crushing zone. The crusher frame rests on rubber supports to reduce vibration transferred to the chassis. Probe control maintains a choke-fed condition, improving particle shape and gradation. That steady material column inside the cone changes the quality of the end result. The diesel-electric drive delivers 483 horsepower to the system, with 270 horsepower dedicated to the cone itself. Independent crawler drives allow remote repositioning across the site. An extra-wide conveyor with a high discharge height moves processed aggregate efficiently, while dust protection through an overpressure system keeps components shielded during heavy production cycles. Kleeman MOBICONEMCO11 demonstrates how power, technology, and controlled feed combine in modern secondary crushing. Swing the wrecking ball into reinforced concrete and watch entire structural sections collapse in seconds, clearing aging base buildings to make room for new housing. The crane positions the steel sphere above the target wall, then releases it in a controlled arc. Momentum builds through gravity and cable length, driving the ball straight into the facade. Each strike transfers concentrated force that fractures concrete and snaps internal supports. Dust rises as sections give way, exposing steel reinforcement and hollow interior spaces. The operator draws the ball back for another pass, adjusting angle and height to weaken load-bearing points. Repeated impacts focus on corners and joints, breaking structural continuity until floors drop inward. That impact cycle turns solid walls into rubble faster than most expect. Debris accumulates at the base, forming piles for later removal and recycling. Controlled demolition with a wrecking ball follows physics, timing, and positioning to dismantle large buildings methodically without explosives. A Phase 1 concentrator is already sustaining over 500 tons of copper per day during ramp-up. Underground ore is hauled to the surface and reduced through crushing and grinding before entering flotation cells. Milling throughput has exceeded 80% of design capacity, while copper recovery climbed from roughly 70% to about 81% within a month. Higher recovery means more saleable metal from the same tons of ore. That jump shifts revenue potential in a noticeable way. Roughly 700 tons of concentrate have been dispatched for smelting into blister copper, forming traceable units ready for delivery. Underground development now stretches beyond 52 kilometers, well ahead of plan. Output at this scale truly resets expectations.
Many demolition crews rely on one breaker, but the Indeco, HP 25000, ISS 3050s, and IRP 1250 show why multiple tools matter. The Indeco HP 25000 hydraulic breaker mounts onto a high-reach excavator and lines up with thick structural walls. The tool drives repeated impact energy straight into the concrete mass. High impact force concentrates stress inside the slab until fractures spread outward. Rebar becomes exposed as chunks separate and fall away. That first break hits hard. Debris is cleared to open space for the next strike. The HP 8000 moves into tighter sections. Its smaller frame allows controlled removal around confined structural elements. Compact breaker geometry supports access without sacrificing striking power. Concrete edges are trimmed down to manageable sections. For secondary reduction, the ISS 3050s shear grips protruding steel, hydraulic jaws close firmly, and slice through reinforcement bars. Shear force converts hydraulic pressure into direct cutting strength on steel members. Steel pieces drop free for sorting. The IRP 1250 rotating pulverizer follows to crush remaining fragments. Its rotating head positions the jaws exactly against stubborn sections. Oh, that crushing bite finishes the job cleanly. Rotational control improves material processing efficiency and reduces oversized debris. Step by step, structural components are broken, cut, and reduced into transportable material. Basic tools and open yards produce clay bricks strong enough for multi-story construction. Brick density and compressive strength depend on proper clay preparation and forming pressure. Raw clay is delivered and spread across the yard to dry slightly under open air. The screening machine separates large clumps and removes stones automatically. Screen mesh size determines the maximum particle dimension allowed into production. Water is added gradually, and the mixture is turned until it reaches a workable consistency. Moisture content directly influences plasticity during molding. Controlled water dosing stabilizes the clay body during extrusion. The texture has to hold shape without sticking. Uniform mixing distributes water evenly through the clay mass. Homogeneous blending reduces weak zones inside the formed brick. The balance matters more than it looks. The prepared clay is pressed into rectangular molds. Consistent molding pressure determines final brick density. Forming equipment applies steady compression across the full brick profile. A wire cutting system divides the long clay column into individual bricks with clean separation lines. Tension cutting wires maintain straight, parallel faces on every unit. Cutting speed must match extrusion rate to keep dimensions consistent. The shaped bricks continue drying until they reach suitable moisture content for the kiln. Many crews swap full attachments for each task, but a single excavator fitted with the Dehako MS130R multi-system handles demolition, sorting, and recycling by switching jaws only, without changing the carrier machine. The Dehako MS130R multi-system centers around a main body designed for interchangeable jaw sets. One configuration functions as a concrete shear for structural removal. Another jaw set converts it into a pulverizer for breaking reinforced sections. A different pair handles scrap cutting, while combi and plate shear options expand its range. That flexibility changes the workflow completely. Wow, one body doing all that. Modular jaw exchange minimizes machine downtime between demolition phases. Fewer attachment changes also reduce wear on couplers and hydraulic connections. The compact and slim design supports better visibility from the cab. Improved sightlines allow more accurate positioning during material separation. A 360-degree hydraulic rotation system lets the tool align precisely with the target area. No awkward machine repositioning required. Dual hydraulic cylinders keep the shear centered during operation. Self-centering action reduces torsion on the boom and lowers stress on the rotation ring. Under load, balanced force distribution protects structural components while maintaining cutting strength. The result is controlled demolition and efficient material processing using one adaptable system. A drilling rig drives steel casing beneath a road and completes a groundwater well without cutting the surface. The operation positions the drilling rig at the marked point and advances the rotating drill string into the ground. Cuttings and slurry rise along the borehole and are lifted out continuously. Removing excavated mud keeps the borehole clear for steady penetration. Depth increases section by section until the target water layer is reached. Wow, that vertical progress adds up fast. During underroad drilling, alignment is controlled to pass beneath the surface without disturbing traffic. Stable bore walls maintain the design diameter throughout the shaft. Once drilling reaches full depth, casing pipes will be lowered into the borehole.
Follow the relocation of the CAEX 798 and understand exactly how 286 tons travel 138 kilometers safely. The unit is positioned onto a 12-axle modular platform rated for 363.5 tons. That axle distribution spreads weight evenly and protects the road surface. Hydraulic suspension adjusts height and balance before departure, locking the massive frame in place. 3 tractor trucks connect to the front, delivering a combined pulling capacity of 600 tons. Using multiple tractors increases traction and control on gradients. Transport covers 138 kilometers, requiring route planning that accounts for turning radius and bridge limits. A narrow section becomes the critical point of the journey. Clearances tighten, speed drops, focus sharpens. Wow, that squeeze leaves almost no margin. Upon arrival, dimensional measurements verify transport stability. Recorded height reaches 10,116 millimeters against a calculated 10,068 millimeters. Final verification confirms structural integrity after relocation. Heavy haul logistics at this scale leave no room for guesswork. The dirtier the culvert, the more efficient a culvert jet becomes under sustained pressure. Recycled water fills the supply tank before operation moves forward. Using reclaimed water reduces consumption without lowering cleaning force. A high-capacity pump pressurizes the flow, sending it through reinforced hoses toward the jetting nozzle. The nozzle enters the culvert slowly, directing concentrated streams backward and sideways. That backward thrust pulls the hose deeper, while breaking apart compacted sediment. Jet angles are engineered to cut debris and flush it downstream in one coordinated action. Mud, sand, and organic buildup loosen and travel toward the outlet. The blockage clears quicker than you'd think. Continuous pressure maintains scouring power along the pipe walls, stripping residue that restricts flow. Consistent jet force prevents partial cleaning that could lead to repeat clogs. Once the interior runs clear, water circulation continues briefly to verify unobstructed discharge. Clean passage restored, drainage capacity returns to full performance without freshwater waste. Follow the Fent 516 Profi Plus and LBH Canfris operation to see exactly how drainage stability is restored. The Fent 516 Profi Plus supplies stable hydraulic output to power the LBH Canfris mounted at the rear. Consistent hydraulic flow keeps cutter speed steady under load. The cutting drum lowers toward the roadside edge, targeting compacted soil and overgrown buildup that block water runoff. That controlled engagement protects the road base while removing obstruction efficiently. As the tractor advances, the Canfris trims a defined channel along the ditch line. Soil and vegetation lift and discharge to the side in a controlled stream. Opening that edge allows surface water to leave the roadway instead of pooling on top. Without proper drainage, gravel weakens quickly. No wonder ruts form after heavy rain. Blade depth adjusts through the tractor controls, adapting to varying shoulder height. The operator maintains a straight pass to ensure uniform ditch geometry. Uniform shaping improves long-term road stability and reduces repeated grading. Material removed from the edge remains windrowed for later redistribution or collection. The second pass refines the slope, smoothing transitions between driving surface and ditch. Wow! The difference shows up immediately once water has a path to follow. Tire tracks stay centered while the shoulder gains a clean profile. Throughout the operation, engine torque from the Fent 516 Profi Plus supports steady forward motion without sudden surges. The LBH Canfris maintains cutting force against packed gravel and roots. Balanced tractor power and cutter resistance prevent uneven trench depth. This coordinated setup reduces strain on components and improves operational efficiency over long distances. By the final stretch, the gravel road carries a defined drainage line along its edge. Water can exit efficiently, structural integrity improves, and maintenance intervals extend. A straightforward pairing of tractor and edge mill delivers a practical solution built on mechanical control and measured ground engagement.